Hello everyone. In this video I'm going to show you how to solve the problem number 3 and 4 of the midterm exam. For problem number 3 we need to find the angle of arrival of the root locus branches at the zeros, both for the positive locus and the negative locus. The transfer function which is provided for us is given as 7.5 times s squared plus 4s plus 5 squared over s plus 3 squared times s plus 3 squared, and the controller is a proportional one. So basically what we need to start with, since we only are going to find the angle of arrival of the branches at the zeros, is to first determine the location for the zeros of the system and the open loop poles of the system. For the zeros of the system, we have the roots of s squared plus 4s plus 5 squared equal to 0. This means that we will have four zeros first of all, s1, s2, s3, and s4. And they will be located at minus 2 plus j, minus 2 minus j, minus 2 plus j, and minus 2 minus j. So there will be 4 zeros for the system. For the poles of the system, it's quite easy. So we have s plus 3 to the power of 4 equal to 0. So we will have s1, 2, 3, and 4. All of them will be located at minus 3. So we have 4 poles at minus 3 and 4 zeros at minus 2 plus minus j. Now we can start to draw. We have the real axis and imaginary axis. We have minus 3 here, minus 2, so the zeros that we have are located here. We have 2 zeros here, 2 zeros here, and we have 4 poles at the point minus 3. Now, if we want to, since we are going to find the angle of arrival of the root locus branches at the zeros, we will apply the phase condition, which is phase of n over d equal to phase of minus 1 over rho in the vicinity of the 0. So let's do it for the 0 at minus 2 plus j, which is this point. I'll take a test point here, very close to that 0. Then we will find the angle between that point and any of the poles and zeros of the system. The first one to consider is the zeros which are nearby. So this will be indeed the alpha or beta arrival. Since we are considering the angle of arrival, so we will call it beta arrival. We have beta arrival, and we have 2 of them because we have 2 zeros there. Then the next angle to consider is the angle between these 2 zeros and the test point over there, which is equal to pi over 2. And the last angle to consider is this angle that we have between the poles and that test point. And since we have 1 here, this will be equal to pi over 4. And keep in mind that we have 4 of them over here. So for phase of n over d, we can write it in the form of phase of n minus phase of d. For phase of n, we will have 2 times beta arrival, which come from here, plus 2 times pi over 2. So this will give us 2 beta arrival plus pi. For phase of d, we will have it as 4 times pi over 4, which will be equal to pi. Now we have phase of n minus phase of d equal to 2 times beta arrival plus pi minus pi, and that will be equal to the phase of minus 1 over rho, which is equal to 2h plus 1 times pi and 2h pi for positive locus and negative locus, and we will have h equal to 0 and 1 as we have two zeros at that point. So we will have beta arrival being equal to, this will cancel out. If I replace h with 0, we'll have pi and 3 pi divided by 2 for positive locus, and 0 and 2 pi divided by 2, which will be equal to pi. So beta arrival will be equal to pi over 2, 3 pi over 2 for the positive locus, and 0 and pi for the negative locus. Let me maybe show the angles here on a separate graph. This is what we are going to have for the positive locus, and another one for the negative locus. We have two zeros, 4 poles, 2 zeros and 4 poles. For the positive locus, we will have pi over 2 and 3 pi over 2. So the branches will arrive like this, with the angle of pi over 2 and with the angle of 3 pi over 2. And since we have it for those zeros, we will have the mirrored ones for the zeros downwards. For the negative locus, they will arrive with these angles of 0 and pi. We can also find the angle of departure from the poles that are here, and then based on that we can find the complete Root-locus plot for this system, but that's beyond the requirements that we have for this problem. You can maybe try to find out the complete body plot for this, the complete Root-locus for this system, and then you will see that it verifies our findings in terms of the angle of arrival. The next problem, problem number 4, is regarding finding the angle of departure from the poles of the system. The system now is another one, so we have s squared plus 2s plus 2 over s squared plus 6s plus 10. We'll have 4 zeros and we'll have 4 poles. The zeros will be located at -1 plus minus j and -1 plus minus j. And the poles of the system, the poles of this system will be located at -3 plus minus j, -3 plus minus j. And we are interested in finding the angle of departure from the poles. So we have double zeros here, double zeros here, double poles here, and double poles here. Now, to find the angle of departure from the poles, we need to apply the angle condition or phase condition in the vicinity of the pole over here. We'll have phase of n over d equal to phase of -1 over rho. And phase of n over d will be equal to phase of n minus phase of d. For phase of n, we will connect this point, this test point, to all the zeros. So we will connect the point to the zeros and the horizontal line from the 0 towards the plus infinity. And we'll get the angle here. So we'll have pi here, and this angle will be 3 pi over 4. So for phase of n, we will have 2 times pi plus 2 times 3 pi over 4. And this will be equal to 2 pi plus 3 pi over 2. For phase of d, on the other hand, we need to connect this test point to the poles. So we'll have alpha departure, 2 times alpha departure here, and there will be pi over 2 here, and we'll have 2 times that, so we'll have 2 times alpha departure plus 2 times pi over 2. This will give us 2 alpha departure plus pi. So now if we plug the values that we have for n and d into the phase condition equation, we will have phase of n minus d. So for n we will have 7 pi over 2 minus for d we have 2 alpha departure plus pi, and this will be equal to 2h plus 1 times pi for positive locus and 2h pi for the negative locus, where we have h equal to 0 and 1. And now we just need to simplify to obtain the value for alpha departure. 7 pi over 2, let me rewrite it, 7 pi over 2 minus 2 times alpha departure minus pi is equal to, if I replace h with 0 and 1, so we'll have pi, 3 pi, 0, 2 pi for positive locus and negative locus. And then out of here we will have 7 pi over 2 minus pi will give us 5 pi over 2 minus 2 alpha departure will be equal to pi, 3 pi, 0 and 2 pi, positive locus, negative locus. Then we will have minus 2 alpha departure will be equal to the values that we have here minus pi over 2, so minus 5 pi over 2. So we'll have pi minus 5 pi over 2, 3 pi minus 5 pi over 2, 0 minus 5 pi over 2, and 2 pi minus 5 pi over 2 for the positive locus and negative locus. And this will be equal to minus 3 pi over 2, pi over 2, minus 5 pi over 2, and minus pi over 2. Now we just need to divide both sides with minus 2. And therefore we will have alpha departure will be equal to, if I divide everything with minus 2, we'll have 3 pi over 4 minus pi over 4 for the positive locus, and 5 pi over 4 and pi over 4 for the negative locus. Now I can also show it on the S-plane how we will have the angle of departure from the pose for the negative locus and positive locus. We have 2 zeros and 2 pose here and there, so 2 zeros, 2 pose. For the positive locus, the angle of departure will be 3 pi over 4 and minus pi over 4, so we will have this angle and this angle for the departure of the branches from the pose. Basically, if you complete the drawing, it will be somehow like this. Okay, but that's not what we are supposed to do here. It will be something similar to that. For the negative locus, on the other hand, we will have 5 pi over 4 and pi over 4 for the pole that we have here. So 5 pi over 4 will be this angle, and pi over 4 will be this angle. For the negative locus, we know that all the real axis belongs to the negative locus, and therefore the branches that departed the pose, two of them will arrive at the real axis. One will go towards plus infinity, the other will go towards minus infinity, and the other two branches that we have here will arrive at the zeros. We can find the angle of arrival at the zeros, but on the other hand we have two zeros here, so there will be another branch arriving at this. Basically, we have this branch moving towards plus infinity, the other branch goes towards minus infinity, but here we have no asymptotes. Therefore, that branch will come back towards the origin from the positive side. At some point, it will meet the angle coming from here. They will depart the real axis, and then they will arrive at the zeros, because you should remember that we have no asymptotes in this case. Alright, so but those are the details that we are not interested in for this problem. We were supposed to find out the angle of departure from the pose, and we are done with that. Okay, so I think that's all for this video. Thank you for watching, and see you in the next video.